Alrighty, so we're doing another one on the sway potential here, and this is a follow-up on when we had potential that was what's the word? Symmetric about x equals 0, so that's 0 there, and we had it going from minus L on 2 to L on 2. And what we will do in this one is look at what happens when this is expanded to twice its length. So say a particle was originally prepared in the ground state, and so it looks like this, and we expanded the potential well sufficiently fast enough to not change this wave function, and then we go to measure it. So what is the probability of it being in one of the new states, say the ground state of the new well, or the first excited state, and so on? We have to use Fourier analysis to find out what the probability values are. So we remember from before, wrong color. We had two solutions for the wave function. So we had our odd solution, that's for odd n, and our even solution, that is for even n. Okay, so say we prepared our particle in the ground state originally, so we have a superposition of all our basis states that we need to project our original wave function onto. And what was our original wave function? It was cosine, and n equals 1, so it's pi x on L. We're projecting that onto our basis states that are in superposition, so we have to add them all together. And we have an here, cosine pi x. Okay, now to find, again, we know how to find these using Fourier's trick, and we have to choose an orthogonal wave function that will give us a non-zero answer when we use the orthogonal properties. So a good idea is to use cosine, because we have a cosine on the left. If we use sine, when we get 0 here, and we would get a non-answer here, or trivial answers. So we know that this will go away once we use cosine. So we can simplify the expression here. So times both sides by our orthogonal function, and integrate piecewise where we have a non-zero answer in the integral. Now we remember also from the orthogonality principle that when n does not equal m, it returns 0, so we have to do for when n equals m. We change these to this, which makes this simplify nicely. Actually, just write that here. Looking at the integrand only, that becomes this using our trig identity. So there should be 2 and 2L. The 2's disappear, and we can integrate this and we'll find that that equals L. So I'll put that in up here. Discovered that integral equaled L. But now we rearrange to find what these coefficients equal. And what do they equal? Okay, and that's what we have. Now we can use another trig identity, again, that we've seen in previous videos. So what can we make this into that would be easier to integrate? And I will also make the integral easier by doing this. So we get a 2. That 2 cancels with that 2. That becomes a 3. L plus okay. So we'll put in our numbers. Oh no, we have to integrate first, of course. So this becomes a whole heap of numbers. Now I'm running out of room, so I'm going to clear some of this. Okay, so what does this all equal when we put in our numbers? This is not too hard, so I don't have to explain much as I go along. That's a 3 n pi on 4. Okay, so we want to see what happens, what would this coefficient equal if, let's see, what's the probability of this coefficient being in the ground state? So we'll see a 1, so wherever we see an n we put a 1 in. Oh, and I think we can get rid of that L, it cancels with that L, that one as well, and you can bring out this n pi. It should not be next there. Okay, so we get 2 root 2 on pi 2/3, and when n equals 1, this sign becomes a 1 on root 2. We remember our trig triangles. Plus 2, and again this one is also a 1 on root 2. We can simplify this down to 8 on 3 pi, and to find our probability, if you remember from before, probability is the norm squared of this coefficient, so that equals 8 on 3 pi squared, which approximately equals numerically 0.721. So we have a about 72% chance of the ground state on measurement. There you go.